So imagine for a second that we just removed a single chemical element from our modern world. I mean, the results would literally be instant and catastrophic. An eerie silence would fall over global trade. Massive cargo ships, they just vanish mid-ocean, dropping millions of shipping containers straight into the waves. The bridges spanning our biggest rivers would instantly lose their structural framework and plunge into the water below. Our towering skyscrapers would crumble into dust the second the internal rebar skeleton holding the concrete together just ceased to exist. Global supply chains would snap overnight, and the intricate industrial machinery that makes, well, almost everything we consume would just stop. Welcome to This Explainer. Today we're diving deep into the absolute foundational material of human civilization.
But there's a really fascinating twist to this whole scenario. If you look closely at those vanishing railways, ships, and skyscrapers, most of those things aren't actually made from the pure element itself. Instead, they're made from materials based on it, materials that serve as the invisible skeleton of modern life. And the absolutely crucial one there is steel. But here's the undeniable truth. Without iron, there is no steel. And without steel, the industrial world as we know it would be radically, completely unrecognizable. So what exactly is this stuff? Where does it come from? And how on earth did humanity figure out how to bend it so perfectly to our will?
All right, let's get into it. On a totally fundamental level, iron is a chemical element. It's a transition metal sitting right at atomic number 26 on the periodic table. That just means every single iron atom has exactly 26 protons in its nucleus. But its importance goes way beyond human technology. It's actually central to our geology and our very survival on this planet. Earth contains an absolutely staggering amount of it. In fact, right now, beneath our feet, there is a churning, superheated ocean of liquid iron and nickel that makes up our planet's outer core. And the immense currents of that sloshing liquid iron, they are what actually generate the Earth's magnetic field. That's the invisible shield protecting our atmosphere from being completely stripped away by deadly solar winds.
If you check out the periodic table, you'll see it listed by its symbol, Fe, which comes straight from its old Latin name, ferrum. But knowing where the name comes from brings us to this grand cosmic joke played on early human engineers. See, despite the fact that iron is incredibly abundant and makes up a massive percentage of the Earth's mass, you almost never walk outside and find shiny metallic iron just sitting in the dirt. You can't just pick a chunk up off the ground and forge a sword or a wrench out of it. It's hiding in plain sight. Why? Because iron reacts intensely and rapidly with other elements, especially oxygen. Because it loves oxygen so much, getting to the pure usable metal requires a massive technological intervention. The process of extracting iron isn't just some basic checklist. It's this meticulously choreographed metallurgical symphony that humanity had to develop through thousands of years of painful trial and error. To get iron, we have to mine and crush rock, heat it to insane temperatures, completely manipulate its chemistry, literally tear the oxygen away, and then meticulously control the carbon. It absolutely boggles the mind that ancient humans, who had zero understanding of modern chemistry, managed to figure out this sequence to turn ordinary-looking dirt into the versatile platform that built our modern world.
And this perfectly illustrates what miners are actually dealing with. When we mine for iron, we aren't digging up chunks of ready-to-use metal. We're extracting iron ores. Specifically, we're pulling up compounds where iron is chemically locked in a super tight, unyielding embrace with oxygen. Two of the most important minerals we rely on globally are hematite and magnetite. If you think about their chemical formulas, Fe2O3 and Fe3O4, you realize they're just absolutely packed with oxygen. To get the usable iron out of them, we essentially have to pull off a chemical heist. We literally have to steal that oxygen away from the iron atoms.
Now that chemical heist actually has a scientific name. It's called reduction. Simply put, it's the process of removing oxygen from a compound. Learning how to perform this exact transformation reliably was, without a doubt, one of the greatest technological leaps of the ancient world. I mean, think about how counterintuitive this discovery was. Early smiths had to realize that if you heat iron ore alongside burning charcoal, the wood doesn't just make things hot. In a low-oxygen environment, it creates an invisible gas, carbon monoxide, and that carbon monoxide acts as the thief. It wages a microscopic chemical war, reacting with the iron oxides violently pulling the oxygen away and leaving behind that pure metallic iron we crave.
But obviously, humanity didn't just master this whole process overnight. Interestingly enough, some of the very first iron ever used by humans didn't require this complex reduction process at all. Why? Because it literally fell from the sky. Ancient people would occasionally stumble across these rare, nickel-rich meteorites that contained ready-to-work, pure metallic iron. Ancient royalty, like the pharaoh Tutankhamun, were actually buried with daggers forged directly from fallen stars. How cool is that? But space rocks are incredibly scarce.
To actually change civilization, by the 2nd millennium BCE, humans developed bloomery furnaces. These used charcoal to separate out the oxygen, but they just couldn't get hot enough to completely melt the iron. Instead, they produced this hot, glowing, spongy mass of metal and slag called a bloom. Blacksmiths then had to painstakingly beat this hot mass with heavy hammers over and over to squeeze out the impurities and create wrought iron. Fast forward to the modern era, and we scaled this concept up to massive, towering blast furnaces that could continuously produce an actual flowing river of liquid metal. But here we run into one of the greatest ironies of metallurgy. Pure iron, just on its own, is actually relatively soft. To make it strong enough to literally build a world, you have to add carbon. Think of carbon in iron a bit like salt in a pot of soup. If you have too little, it's soft and weak. But remember those blast furnaces we just talked about? Well, they use massive amounts of carbon, things like coke and charcoal, to strip away the oxygen. During that extreme process, the liquid iron absorbs way too much carbon. This creates what we call pig iron. Pig iron is incredibly hard, but it's dangerously brittle. It's like dumping a whole cup of salt into your soup. So to make the perfect steel that builds our skyscrapers, engineers have to take that carbon-rich pig iron, painstakingly burn out almost all of the carbon, and then meticulously add back an exact microscopic amount. Creating steel is really an exercise in extraordinary, Goldilocks-level chemical control.
Let's zoom in on the physical constants of this material for a second, starting with its density. 7.87 grams per cubic centimeter. Imagine lifting a solid block of iron in one hand and then lifting the exact same sized block of aluminum in the other. The iron feels incredibly heavy, substantial, and dense. It's roughly 3 times denser than aluminum, which, by the way, is exactly why we don't build commercial airplanes out of it. But that immense density and heft translates directly into the sheer structural fortitude that allows us to span vast distances across rivers and effortlessly support thousands of tons of concrete in our cities.
And then there's its staggeringly high melting point, 1,538 degrees Celsius. That extreme temperature is the exact reason it took humanity centuries of furnace innovation to truly master this metal. Early civilizations can melt copper and tin to make bronze over a relatively simple fire, which is why the Bronze Age came first. But ordinary wood campfires, they simply cannot reach 1,538 degrees Celsius. Melting iron required industrial infernos. It forced ancient engineers to master thermodynamics, figuring out how to forcefully pump oxygen into specialized furnaces to create heat unlike anything they had ever built before.
Beyond sheer physical strength and heat tolerance, iron possesses this hidden superpower: ferromagnetism. Under ordinary conditions, the magnetic regions inside iron can align strongly, allowing the material to become powerfully magnetized. So the really crucial point here is this. While we often think of iron purely as the heavy metal of hammers, nails, and bridges, it is also the invisible force driving our entire modern electrical world. Every single time you flip a light switch, charge your smartphone, or watch an electric vehicle drive by, you are relying on iron. Without iron's unique ferromagnetic properties, the motors in our EVs, the massive generators in our power plants, and the transformers that bring electricity into our homes just simply wouldn't function. Now, to understand how we manipulate this metal so effectively for all these wildly different uses, we actually have to look inside the atom. Even pure iron doesn't have just one fixed atomic structure. At room temperature, its atoms are arranged in what is called a body-centered cubic structure, or BCC. But if you heat it up high enough, the iron atoms literally physically rearrange themselves into a face-centered cubic structure, or FCC. Imagine a crowded room of people holding hands in a very specific pattern. When the room gets really hot, they completely change their dance formation. In doing so, they suddenly create empty pockets of space on the dance floor. When iron heats up and shifts to that FCC structure, it creates tiny atomic pockets where little carbon atoms can easily slip in and hide.
And this elegantly simple trick of physics explains why that shape-shifting atomic dance is so critical. Different crystal structures dissolve different amounts of carbon. If a blacksmith heats a piece of steel until the atoms rearrange, letting carbon slip into those gaps, and then plunges that glowing hot metal into a bucket of water, a process called quenching, you hear that violent hiss of steam. What's actually happening in that split second? Well, the rapid cooling freezes those carbon atoms tightly in place before they can escape, completely changing the internal microstructure. This is the absolute foundation of heat treatment. It's how we can take the exact same piece of raw metal and decide whether it should be a tough, flexible suspension bridge cable or an incredibly hardened, wear-resistant gear in a car transmission. The human eye sees the same gray metal, but at the microscopic level we have completely re-engineered its soul.
But every material, no matter how strong, has a weakness. And for iron, it's an active, relentless enemy: rust. When ordinary iron meets oxygen and moisture, electrochemical reactions create hydrated iron oxides. Now, other metals like aluminum also oxidize, but when they do, they form a tight, invisible, permanent shield that protects the metal underneath. Iron just doesn't do that. Its rust is porous. It puffs up, weakens, and flakes away, constantly exposing fresh, vulnerable metal to the elements, until the entire structure is literally eaten alive. This is a massive engineering vulnerability. Globally, we spend billions upon billions of dollars every single year fighting a never-ending war against rust. We're constantly painting bridges, galvanizing parts with zinc, or alloying iron with expensive chromium to make stainless steel, all just to delay the inevitable decay.
But zooming all the way back out to the macro scale reveals a monumental modern challenge. Because conventional blast furnace production relies so heavily on carbon, specifically coke and carbon monoxide, to strip the oxygen away from the ore, the direct, completely unavoidable chemical byproduct is carbon dioxide. And because our global civilization consumes iron and steel on such a staggering, almost incomprehensible scale, we are building entire cities and fleets of ships every year. The resulting carbon emissions take up a terrifyingly large slice of global emissions. It actually accounts for nearly 10% of all human-made CO2.
This massive carbon footprint is exactly why modern metallurgy is actively trying to rewrite the rules of extraction. Enter the cutting-edge future of direct reduced iron, or DRI. Think about the chemistry for a second. Instead of using carbon to pull off that chemical heist and steal the oxygen from the rock, engineers are learning to use hydrogen gas. When hydrogen reacts with iron oxide in a specialized furnace, it still successfully strips the oxygen away, leaving behind the pure, solid iron we need. But the real elegance here is in the byproduct. It isn't choking black smoke or carbon dioxide. It's simply water. If a steel plant uses hydrogen produced by low-emission electricity, the chimney would theoretically just emit pure water vapor. That would dramatically transform the environmental legacy of iron-making.
And that really brings our incredible story full circle. Thousands of years ago, early humans staring at strange, heavy rocks were trying to solve one specific puzzle. How do we get the oxygen out of this ore? They solved it with wood fires, then charcoal, then coke, and finally, colossal industrial blast furnaces. Today, humanity is still trying to answer the exact same chemical question, just in a new way. Iron isn't just some ancient relic. It's an extraordinarily versatile platform that gave us steel and, in turn, literally built the modern world. So, can we remove that oxygen differently? Well, the answer to that question will likely decide the future of our climate. Thanks so much for joining me on this explainer. I really hope this changes how you look at the world around you.